So what is neutron activation? Where you can use this analysis to identify or to analyze an unknown sample. So let's give it the unknown sample an element number or name X. So element X is able to absorb excess neutron when it is bombarded with fast or thermal neutron. So with any element, you have a mass number and the atomic number. So there is A and Z. And if it able to absorb neutron, as you exposed it to neutron, it becomes, the nucleus will absorb an excess neutron, and this would be the same. And what happened to an unstable nucleus where the number of protons and neutrons are not equivalent, or they are not in the equilibrium, or they are not stable? What happened to unstable nucleus? They decay. So Y is now unstable. Right? So the unstable Y is A plus 1 and Z. It could decay in many different routes. It could be alpha decay, beta decay, it could be gamma decay. So say that it decays with to get to another element, or you call it a nuclear interaction. It's called as the daughter, and while this being the parent and the daughter. So let's say it decays with gamma, by releasing excess gamma photon. What would the A and Z be for the element Z? It will still be the same because gamma is an uncharged photon. So you get Z here. Now this can further decay if it's still unstable. So any unstable nucleus will force itself to keep on going onto a decay scheme to reach a stable state. So it gave probably to W, A plus 1, Z. Maybe it would release alpha. What is alpha? It's the nucleus of helium. So it's 4, 2. It is now A minus, I'll be minus 3. A plus 1 minus 3. And then this one would be Z minus 2. So this is, let's say, P. And so on. So until it gets to a nucleus that is stable. So these, depending on the half-life of the parent daughter and parent daughter, and each has its own property, which is the half-life and the decay constant, right? Just like any other radionuclide. So now, let's think separately on gamma detector or radiation detector. So what is a radiation detector? There are many different types. There is gas-filled semiconductor, or in our case today, we are going to have a look at scintillator detector. So what is a scintillator detector? It uses a phosphorus or the crystal material that enables to produce scintillation light. So in our case here, we are using sodium iodide. There are many different types of crystal. It could be VGO, LSO, and so on. So here today, we are going to have a look at sodium iodide. So now, if I bring this Y that is unstable, that would decay to Z, and releasing gamma photon, the gamma photon would be able to interact with the sodium iodide detector. Right? So what happens as photons interact with matter? What actually happens? It would either be photoelectric, Compton scattering, and pair production. And pair production only occurs if the energy is more than 1.02 MeV, and here it will be about 0.1 MeV, and this would be Compton. So depending on these incoming gamma photon, it will interact with either of these interactions. So this is the probability of interaction of photons with matter. Alright? So now what actually happens? So depending on the energy, we are not working with high energy photons here, most likely photoelectric or Compton. So what is photoelectric and what is Compton? Photoelectric is when the electron from the most inner shell is ejected out and leaves a vacancy, and the vacancy is filled by the either subsequent orbital electron, or it will be K, L, M, or N. Most likely it will be from L. This electron will be filling in the vacancy, and the difference between these two orbitals will give you a visible light that appears just as the scintillation light. Or Compton scattering could occur with the gamma photon with the sodium iodide crystal. So the gamma photons interact with the sodium iodide crystal through Compton scattering. So what is Compton scattering? When the electrons that are ejected out far away from the nucleus. So K, L, M. So let's say M or N or P. It always occur depending on which electron it could be at. K, L, N, O, P. It could occur with any of these electrons, right? If it occurs at L, electron is ejected out and parts of the gamma photon will go this way and this electron will go that way. This vacancy will be filled in by other electrons. The binding energy at K is way higher compared to the binding energy at L. The difference between the two L and N is short or small compared to K and L. Therefore, the visible light that is to be produced here is in a lower intensity compared to the visible light here. So in both occurrence or both interactions, you would have the presence of scintillation light. So what happened to the scintillation light? The scintillation light here at the sodium iodide crystal, the visible light is either from photoelectric or from Compton. These photons will interact with the photocathode layer of your detector, and at the back here there is a Compton and diodes, and this interaction, the absorption of photons at the photocathode will emit one electron, and this electron will be focused by the focusing up to this diode and to emit more electron, and this electron will go to this side to emit more electron, and you can multiply this electron, and this information will be collected at the anode at the back of your sodium iodide crystal. So based on this information, it will then be processed. The signal is equivalent to the intensity of the incoming photon. If it's high, it is considered to be from photoelectric. If it's low, it will be from Compton scattering. So what actually happens here on your multi-channel analyzer? So in the lab later, you are going to have a system that this sodium iodide can detect all these interactions at the same time and beam the energy separately. If you have done the first experiment for your alpha, beta and gamma, you would realize that you would need to identify only one energy. But in this multi-channel analyzer, it has various of energy and you can beam it to wherever you want. So now the number of channels in this multi-channel is about 1024. It goes from 0 to 1023, and from 0 it's constitute the lowest energy to the highest energy. So as you turn on the detector, the background radiation will interact with your crystal, and the background interaction occurs in low energy. At much lower energy, the interaction or the presence is higher. So the background radiation will be shown on your spectrum here. And then you have Compton. Compton will occur with L and M, M and N, N and L. So they have varied intensity of the visible light. So it could be low intensity, higher, lower, and so on. So you will see that with one interaction, one count is recorded. So anything under the graph is recorded as the number of count. So now here you have background radiation and you have Compton continuum. So under this area, under the curve, constitute the number of interaction occurs due to Compton scattering with the detector crystal. and you have, of course, the photoelectric peak. So photoelectric peak occurs at a specific shell electron, normally K, usually K here, and the energy would normally come from L, the electron that filling in the vacancy. So it will be, most likely it will be here, but it varies either sometimes here, sometimes here, depending on which electron filling in the vacancy, right? But the energy would be almost the same because the binding energy of the K is always the highest. So you have all this count and it will appear like this. So when you see this spectrum, you would know this comes from background radiation, this comes from Compton scattering, that as photons interact with your crystal, and this occur as photoelectric interactions occur. Okay, so that is your crystal. Next, we'll go back here. We want to identify the unknown sample. So how do we do that? We have an unknown sample. Okay, now how do we identify this? First, we have to calibrate our detector system. So how do we calibrate? You take a known source. So you have cesium, you have americium, and you have cobalt. So what is the energy for cesium? 661, 662. Americium 59 plus 27, but this one is more prominent. Cobalt would be
1.23.
1117 1330 keV, right? So now you take the known sample or the known calibration source into your detector system and it will interact. So you have this crystal, you place cesium, and then you set the count say for 300 seconds. And you will be able to observe the cesium, background, fountain, and cesium, right? And then you do it for 300 seconds for 5 times. Then you remove that and replace this with americium. So americium, the energy is lower, so you'll be able to see something like this. Background would be the same, but the energy would be on the lower end. So this would be for cesium, this would be for americium. And then you replace that with cobalt. You have lower background, and then you have higher than cesium, the energy. So towards the end of it. So this would be 1170, 1330, right? But here what you are seeing are just the channel number, but you know all the energy. So if you go to the system and identify this channel number, let's say this is 100, this is 40, this is 140 and 145. Let's say you have identified all the channel number, you can plot the calibration curve. So how do you plot the calibration curve? Alright, you have energy channel number. The first channel number is about 40, and the second one is about 100, and this is 140 and 145. And you know the energy. The energy is about 59 here, and 100, the energy is about 661, 140, 1170, and then 1330. Right? So you have this point, this point, this point, and that point. Then you are able to plot the calibration curve and get something that best fits your curve and identify the R-squared of your calibration curve. Now, based on this curve, you can bring in any unknown source. It will produce gamma photon if it has been activated through neutron activation and release gamma photon. So now, you take your sample 1 into here and you count it for 300 seconds, about maybe 5 times, okay? And from this, what you will see, again, background, peak, but you don't know what, you know the channel number, but you don't know this energy because it's unknown. So you bring in the channel number, let's say M, to here, let's say it is, let's say channel M is equivalent to 80. You bring 80 here, you'll be able to find the energy, and from the energy you will identify what is the unknown source, Y. Now that we know it has worked through the neutron activation analysis, we want to check one of the properties, which is the half-life and the decay constant. So how do you do that? You perform another experiment, which is part 3, to see the decay scheme or the decay route of this source. So how do you do that? You take your sample Y, you measure it, let's say at 10 a.m. for 2 minutes. Right here is at 10 a.m. for 2 minutes. So you get count in count per second. So let's say 100. So you get 100. Wait for about 20 minutes to 30 minutes. So let's say at 10:30, you measure it again for 2 minutes. So let's say the count is now 98. Will be here. And then you wait again at 11 and count for another 2 minutes. And you get, let's say, get 90. So let's say 80. So do it enough. so that you can see how the decay goes down with time. So say the initial is 100, you go and extrapolate this graph to how many number of times that you perform the experiment to 50. So this is how per second. So this is 100. So to go to 50, check the time. Say the time is 12:20. You'll be able to get, this is the half-life. And from half-life, can you calculate the decay constant? Yes. Because half-life is equivalent to longitude over decay constant. Alright, so you'll be able to do that. So basically that is the whole experiment, is to perform an analysis of an unknown sample through neutron absorption analysis by performing a calibration study on your detector and identify the properties, the nuclear properties of the unknown sample. That's it. Any questions? No? Okay, we'll stop here and then we'll go to the lab to see the equipment.